Okay, hi everyone. So, as the title gives away, what I'm going to talk to you about is satellite monitoring. And there are lots of different types of satellite monitoring, but what I'm going to look at today is radar monitoring. So, if you are from a remote sensing or satellite background, apologies. This is kind of targeted at the civil engineering audience. So there'll be a few explanations as to what exactly radar monitoring is. The case study we're looking at today is Waterloo Bridge. So if you know London at all, you'll recognize this as one of the prominent bridges over the River Thames. It's a few hundred meters long, and it takes 2 lanes of traffic in one way and 2 lanes of traffic in the other way, as well as pedestrian loading. It was selected as a case study because of some work that a consultancy was doing on traditionally monitoring the bridge because they suspected that the bridge might have some articulation problems. So as a little bit of an overview as to what we're going to talk about, I've just given you a little bit of a background to Waterloo Bridge itself, a little bit of the motivations as to why we're doing this, an explanation of how the satellite monitoring vaguely works, what we put in for the traditional civil engineering monitoring, and what we put in for the satellite monitoring, a presentation of the results, and then a kind of discussion as to why this may or may not be a good idea. So first of all, I was using a satellite called TerraSAR-X, and this is a illustration of how these satellites image. So they pass in polar orbit around the Earth taking images. They have full global coverage, and in this case, this particular satellite was tasked specifically to collect images over the London area for a period of a year or so. Now, a satellite radar image looks something a little bit like this. It looks kind of like a black and white photo, but it's made up of pixels, and in those pixels you have 2 things. You have an amplitude, the kind of scale of reflective response, and you have a phase measurement. So this is a gross exaggeration or no, oversimplification of how this works, but we can kind of think of each of these things as a sine wave. So the satellite passes over the Earth, and it sends a sine wave down, and it comes back up again, and it collects that and reads it. So if your bridge has moved a little bit, the next time the satellite wave comes down and back up again, there's a shift in phase. And you can equivalent that shift in phase into a measurement. So the important thing to note is that when we're taking these measurements, they are in fact measurements in the line of sight of the satellite. Then what you do is you take a series of these single SAR images, and you pass them through an image processing technique. There's a couple of different types of techniques, but what was used in this particular study was something called persistent scatter interferometry. So persistent scatter interferometry, or PSI, makes use of objects that reflect very well. So we take the objects, for example, these bright spots that have a very strong coherence or strong reflectance, and we monitor those specific points over time and discard any of the less stable points. And so the results of these analyses are something like this, where we're monitoring certain distinct points, and we're monitoring over a series of images. So each image has a timestamp, and between each of those images, there's a shift in wave. So as you can imagine, we're monitoring small-scale movements between each image. Now, what we put on the bridge for kind of normal conventional surveying was a number of different sensors as the bridge was undergoing a wider study. Particularly for what I'm going to talk about today, I'm most interested in these blue points. So each of these blue points are above the pier and next to the suspended span, which is either side an expansion joint, and we've installed automated total station prisms at these points. So we're interested in how those points move over time. Now, this is a radar image. You can see the dark bit in the middle is the River Thames, and each of these things crossing over it are bridges. You can see the London Eye there as well. And so with Waterloo Bridge, we looked at the imagery before doing any of the analyses and noticed that actually Waterloo Bridge itself is not a very reflective object. It doesn't actually reflect radar that well. And in fact, throughout the PhD, I was looking at a number of different bridges of different material, size, and type, orientation, And in the end, all of these kind of geometrical effects, material effects, play some part in how well it reflects. And the thing about satellite monitoring is that a lot of it is down to the actual geometry you're working with, how the satellite passes, the type of material it's bouncing off of, and that kind of consideration. So, for this particular case, we decided to install something that would actively enhance that reflection. So, at each of the, this is a prism, next to each of the prisms, we installed a corner reflector. So, a corner reflector is essentially 3 pieces of metal that help the radar reflect and then bounce back, and then you get a much stronger amplitude reflection. They're pretty cheap, and these ones were designed so that they were made out of aluminium to be a little bit lighter, and are perforated so that it gets rid of water drainage, anything like that. The only thing that I didn't really account for was things like people throwing rubbish over the side of the bridge, possible birds' nests, that kind of thing. But generally speaking, most of them worked quite well, and they were, at the same time as these being installed, they were drilled and fixed into the facade of Waterloo Bridge. They're about this big in size, which is much smaller than what the conventional literature says to use. But obviously, when considering the practical implications of installing a corner reflector onto a bridge, the asset owner wants to keep those down to a minimum size. So we did a theoretical calculation and played around with what should work, and these actually picked up quite well. So as I mentioned, next to each of the corner reflectors, we put an equivalent prism. The automated total stations were located here on one of the piers on an adjacent bridge, and on the other side on a building on the embankment. And so this total station could read all the movements on this side and this one on the other side. Similarly, we have to make sure that the satellites can see the bridge. So I was looking at 2 tracks, satellites ascending and satellites descending. So on one side, we've got the satellite ascending going up, and it can see all of the corner reflectors on this side of the bridge. And the satellite that was passing down could see all the reflectors on this side of the bridge. And it was important to install the corner reflectors so that they're oriented towards the line of sight of the satellite for maximum response. So, once they were installed, you can see each of these bright points corresponds to the location of a reflector. And those are the points we were interested in tracking over time as part of this study. So, initially, we just wanted to look at what is the absolute movement, what are the corner reflectors showing from satellite movements, and compare that to the total station readings. Unfortunately, the party that installed the total station prisms installed reference prisms on the river walls of the Thames. Anyone who's seen the Thames knows it's fairly tidal, so therefore its walls move a little bit in and out. And therefore, the reference prisms couldn't be treated as a reference prism. So that took out the chance of doing absolute to absolute, but I'll show you in the next slide what we ended up doing. The thing I put in, the reason I put in this slide was particularly just to notice a few kind of interesting effects. One, this is the temperature, and these are all the various readings from the different prisms. There's a couple of points that end up being discarded. This one turned out to have various different atmospheric effects that couldn't be corrected for in the image processing. And generally speaking, the readings are taken every 11 days, which is a much coarser rate of reading than what we would generally, as civil engineers, be used to seeing. So, what we ended up doing was taking readings relative to one end of the bridge. Because the reference prisms were no longer in play, what we did was measure relative movement. So at one end of the bridge, treat that as fixed and measure relative to that end of the bridge. And we did that with both the total station readings and the satellite readings to get a comparable result. So in orange, you can see the temperature. In pink, these are the satellite readings. And in blue, this is the ATS readings, which were averaged over, I think they were taken at about every 5 minutes and averaged over a 20-minute window or something like this. But what's interesting to note is that, and this is just one example, I think, of one pier relative to the end, but generally speaking, the profile of all of them followed quite well, with the exception of a couple of anomalous points. But generally, you can pick up this kind of seasonal movement. Obviously, if you take an image every 11 days, you're not going to pick up anything like daily variations. But it does fit quite well. And the later piece of work that we did looks at some of the mathematical analysis around best fit of how these points fit with in comparison between these satellite readings and the ATS readings. So, thinking about a general comparison of the two results, there's a couple things to consider. Firstly, your reference point. In an ATS, you need to find a reference point that your total station can actually see. So that tends to have to be close to the site that you're looking at, and in this case, they were the ones that were installed on the river embankment, which would have been better placed somewhere further away, more stable. For the satellite readings, you can choose your reference point to be anywhere within an image, and it's worth bearing in mind that an image, a single image, is the size of something like London, so you've got a lot of area to play with. However, it's best to pick a point that's close to the site that you're interested in to minimize atmospheric variances across the image. And they're just the kind of things that you need to think about when you're installing these kinds of systems. Secondly, I often get asked by the Earth observation community, why would you put satellites when you could just use sensors? There's a number of reasons, mostly because of things like sensors. You have to access a bridge, you have to find a power supply, you have to decide all of these different things, negotiate these things, get on there, put them on, take them off. Someone has to notice when they stop working and when the power is disrupted, and that doesn't always happen. I worked on a number of different case studies where no one actually noticed that the power supply failed, and then so there's a big gap in readings. Satellites, not to say that they are perfect either, but from the previous image, in the time when we're not getting any readings from the ATS, they give us some idea of what could be happening in between. You don't have to pay for extra equipment. In this case, we installed corner reflectors to augment it, but there are a number of different studies in the literature where people have used satellite monitoring to monitor bridges just using the natural reflections of the bridge itself. It doesn't require closure or the data storage and transmission at site. We don't need a power supply to do it. In terms of the frequency and accuracy of readings, this is kind of where it falls down when you talk to civil engineers. We're obviously not getting readings as often as we would like to. Civil engineers would like it like basically every second possible. But in reality, I think it's worth noting that for what you can see, which is in every 11 days, you can see seasonal variation. It does that very well. And in a sector which is moving quite rapidly, so that we're getting more and more new satellites, increased frequency between readings, and increased resolution, it's something that we as civil engineers should be aware of, so that if we understand this now, we can kind of, as the technology catches up, make the most of these new types of data sets and new satellites coming out. In terms of accuracy of readings, it wasn't shown in this particular study, but another study that we did looked at setting up actual corner reflectors at a fixed site and imposing movements. And the scale of accuracy for these types of movements is in the millimeter scale. Literature says that it can be sub-millimeter in very carefully controlled conditions. But in the kinds of things we were looking at, we were seeing in the 2 to 5 millimeter accuracy range for these types of experiments. And finally, it's worth understanding, when you go into this, the satellite requirements and the image processing requirements. For example, we were talking about the satellite paths relative to the bridge. Now, if the satellite passes in a north-south direction, and your bridge is also aligned in a north-south direction, and you were looking for the thermal expansion, if those two components are aligned, you're not going to be able to pick up movements in that line of sight. So bridges that are oriented east-west are optimal for this type of measurement. Bridges that are oriented north-south generally don't pick up very well. And actually, when looking at the results for this bridge, we could see that on the western side, where it was kind of more optimally oriented, it picked up the profile better than on the eastern side. And then finally, in terms of processing requirements, there are a certain number of limitations. When you use satellite data, you need to consider that you need a certain number of images. They all need to be collected in the same orbit and in the same line of sight of satellite. And those sorts of considerations should be taken into account when you're kind of planning to deliver these types of systems. So just to wrap up, as you can see from what we've showed, that there are some really exciting opportunities for satellite monitoring, especially for things that are really remote to access and that we don't really monitor that often. So here in the UK, we tend to do things like highway bridges are inspected every 2 to 6 years. Every 2 years, where you have a general inspection where you can physically see the bridge, and every 6 years we're actually close enough to touch it. So in that period between the 2 and 6 years, you have a data source giving you some kind of insight and understanding. And also at a time where we're seeing increased changes due to climate change and a number of different like anthropogenic effects, it gives you some kind of insight in between these readings. Secondly, it's something that gives you global coverage. Satellites pass over every point of the Earth. I'm not saying they actually turn the satellites on and collect over every point of the Earth, but in theory, we do have that opportunity. As I mentioned earlier, with new satellites, we get new resolutions and increased frequency. And as we showed with Waterloo Bridge, certain bridges that don't reflect very well, we do have this opportunity to retrofit and augment them with corner reflectors. It should be stated that that only works for certain types of bridges. You need a bridge that naturally doesn't reflect very well. You can imagine if it was something metal and spiky and reflects really well, it has a high amount of clutter, and so putting a reflector in the middle of noise is not going to be seen. Finally, it's worth considering that satellite monitoring is very useful for certain types of things. There's a lot of history using it for things like tunnel monitoring, where it picks up vertical movements quite well. With bridges, there is some understanding of material and geometry that needs to be taken into account before you set it up. And finally, the most important thing, I think, for me is marrying up the considerations of the civil engineer with what the satellite observation community thinks. The satellite observation community is quite used to processing large stacks of data and seeing what insights is within the data, whereas we are looking for very specific points in very specific intervals. And really, the value comes from both communities understanding what each other is looking for and making the most of that, the opportunities that we have. And finally, just want to say thanks to a number of different project partners that helped set this up and provided some support for the processing. Thank you.